Welcome to the presentation of the paper, A Monolithic Hardware Implementation of the Kyber, Comparing Apples to Apples in PQC Candidates. My name is Mojtaba Bishen-Niasar, and this is a joint work with Reza Azardarakhsh and Mehran Muzaffari Kermani. In this presentation, we have a brief introduction about the post-quantum cryptography and different implementation strategies. After that, we'll present our proposed architecture to implement Kyber over ASIC platform. After that, we will see our implementation results and we will compare our result with previous works. At the end, we have a conclusion. Let's start with the motivation of this work. As you know, the classical crypto systems, such as the RSA and ECC, will be broken when we have a large scale of the quantum computers. Therefore, we have to immigrate to post-quantum cryptography. Several post-quantum cryptography schemes have been submitted to the NIST competition. To choose the best scheme, the hardware accelerator plays an important role to show differentiation between these schemes targeting different platforms and different applications. Although there are several hardware-software implementation of the PQC scheme, there is only a few pure hardware implementation of them. As you know, the pure hardware implementation can result in better performance using fewer resources compared to the hardware-software co-design approach. On the other hand, there are several optimization perspectives, such as the power consumption, efficiency, performance, and area utilization to compare between these schemes. Additionally, since FPGA has a various type of the hardware resources, such as the DSP and block RAM, to calculate the total area, calculating the total area for these schemes is not straightforward. Therefore, without a common foundation, apples will be compared with the orange. In this work, we compare the efficiency of different schemes or ASIC platform as a common foundation to have a fair and apples-to-apples comparison between these schemes. We implement the Kyber as a finalist in round 3 NIST competition. As you know, this scheme is based on the modular learning with errors. We implement a dedicated core instead of a unified core for several schemes to make all the best for Kyber features. The previous Kyber implementation can be categorized in 3 different strategies: software architecture, hardware-software co-design architecture, and also pure hardware architecture. The first hardware implementation of the Kyber was proposed using HLS-based architecture. After that, several RISC-V architecture were proposed targeting different optimization perspectives, such as the power consumption, performance, and area utilization. Recently, Jing proposed the compact pure hardware implementation of the Kyber. Our research team also proposed the fastest design for the Kyber using highly optimized NTT core. We also proposed an instruction set architecture for Kyber to increase the flexibility of the pure hardware implementation to integrate with other schemes to generate a hybrid crypto system. This figure shows an estimation of performance and resource utilization of the Kyber implementation targeting different platforms. As you can see, hardware accelerator can reduce the latency of the Kyber by absorbing the catch-up latency and other operation. You can see also that that pure hardware implementation can significantly result in better performance compared to the hardware-software co-design, and also it needs fewer resources by abstracting the controller. In this implementation, we proposed a Kyber key exchange mechanism over ASIC platform. We propose an efficient entity core using a reconfigurable architecture which can be used for both entity and inverse entity operations. Our implementation can result in higher throughput using fewer resources compared to the previous works. We also implement a highly parallel architecture which can absorb the latency of the catch-up and sampler units. Our results show more than 96% efficiency improvement compared to the best previous Kyber implementation or ASIC platform. For the NIST security level 1, our implementation can perform key generation, encapsulation, and decapsulation in only 21, 33, and 50 microseconds. In our proposed architecture, we implement two dedicated buffer for catch-up core. Serial input parallel output and parallel input serial output buffers located before and after the catch-up to reduce the latency of catch-up interfacing. This architecture results in the efficiency improvement by reducing the latency of the catch-up operation. As you know, the Kyber implementation needs two different values for eta. Therefore, we implement an optimized configurable architecture for binomial sampling, which can be used for both values of eta. This figure shows our configurable architecture, which can be used for both eta equal to 2 and 3. Although public key is not secret, and we do not need to implement a constant time rejection sampling unit, you know that most of SCA evaluation can be performed on constant time implementation. For example, TVLA or t-test evaluation can be performed only on constant time operations. Therefore, we perform a constant time rejection sampling unit to form a constant time implementation. We calculate the failure probability of the rejection sampling considering regarding different round of the catch-up. And as you can see, performing 4 rounds of the catch-up results in negligible failure rate in rejection sampling unit. The polynomial multiplication in lattice space string can be efficiently performed in entity domain. Therefore, our polynomial should be converted to the entity domain by multiplying its coefficients with the Tweedle factors. After pointwise multiplication, the results should be converted back to the normal domain from entity domain by inverse entity operation, which is shown by this formula. There are two different butterfly configurations which can be used for entity and inverse entity operations. The data flow graph for pointwise for polynomial multiplication of degree 8 is shown in this figure. As you can see, performing CT butterfly for entity operation and GS butterfly configuration in inverse entity operation can avoid the bit reverse permutation in polynomial multiplication and results in better performance. Therefore, we use a configurable butterfly core to have both these configurations. Our entity architecture includes 2 RAM blocks, 1 address generator, a pre-computed RAM for Tweedle factor, and 1 reconfigurable arithmetic unit, which is shown in this slide. As you can see, this architecture can work in 3 different modes. When mode is equal to 0, it works in the entity using CT configuration. When mode is equal to 1, it works in the entity, inverse entity using GS configuration. And when mode is equal to 2, it works in the pointwise multiplication. By implementing two parallel entity architecture, you can reduce the latency of the entity operation to n by 2 log n by 4. We also actually implement different optimization techniques, such as a double bandwidth scheme, to reduce the total area and required memory for our entity architecture. Our results for 65 nanometer technology over ASIC platform is shown in this table. Our design is based on the VHDL and is synthesized by Synopsys Design Compiler. To calculate the total time, we assume that key generation can be performed offline. Therefore, we only add the encapsulation and decapsulation operation. Considering the NAND gate specification in 65 nanometer library, we calculate the gate equivalent of our architecture to have a fair comparison with the other works regardless of their technology. As one can see, our implementation for the Kyber in the NIST security level 1 needs only 95 kilo gate equivalent and 10 kilobytes SRAM. This implementation can perform encapsulation and decapsulation in 83.9 microseconds, working on 200 megahertz. The area and timing breakdown for Kyber implementation is shown in this slide. As you can see, ketchup is the most resource-consuming block in the Kyber implementation, requiring 25% of the total area. However, its latency can be absorbed using a highly parallel architecture with sampling units. Using the compact version of the ketchup leads to the considerably more delay in total performance, which therefore we use the high performance ketchup core in our implementation. In the timing breakdown, you can see that the butterfly unit is the most time consuming operation in the Kyber implementation, requiring almost half of the total latency. However, it needs only 4% of the total area. One can reduce the latency of the entity operation by using more parallel entity architecture. However, this method is more challenging because of the memory bandwidth limitation and also complexity of memory access pattern using a more parallel entity block, butterfly block. For the sampling units, you can also see that it needs only 13% of the total resources, while its latency can be considerably absorbed using the highly parallel architecture. In this table, we compare our entity implementation with the other hardware-based entity implementation of the Kyber. As one can see, our entity implementation needs fewer resource cycle count compared to the most of the previous work. However, there are two faster work in this table. Zheng architecture needs shows 70 times speed up compared to our design in terms of the cycle, while it needs more than 100 times resources compared to our entity block. Our previous work also shows 31% performance improvement using a merge layer of the entity occupying a 2x2 butterfly architectures. This figure compares the Kyber performance using different platforms. As one can see, our proposed ASIC architecture shows almost 3 times slower compared to the Intel Core i7 CPU working at 3.5 gigahertz. However, our ASIC implementation shows more than 600 times faster compared to the Cortex M4 discovery board working at 24 megahertz. This speedup can be achieved using the highly parallel architecture in our hardware implementation. In this table, we list the previous ASIC implementation of the Kyber in all 3 security levels. We also report their area utilization in gate equivalent to have a fair comparison between different schemes. As one can see, our implementation needs fewer resources compared to all previous works. You can also see that our design is fastest design compared to the previous work. To have a fair comparison, we add an efficiency matrix in terms of the area time product, and these results show that our implementation outperforms the previous work in all 3 security levels. This figure is used to visualize the comparison between ASIC implementation in the NIST security level 1. As one can see, our implementation reduced the required logic gates and SRAM requirements of the Kyber implementation compared to the previous ASIC implementation of the Kyber. We can also see that our implementation results in more than 5 times speed up compared to the fastest previous work. To conclude, our implementation can achieve 96% efficiency improvement compared to the best previous work over ASIC platform. To have a comparison with the other PQC implementation in the NIST security level 1, we report the Psych, FrodoChem, and Saber hardware results in this table. As one can see, our implementation needs fewer resources compared to the Saber on ASIC platform. However, Saber shows better performance working at 400 megahertz. You can see also that the performance of our Kyber implementation outperforms the Psych and FrodoChem in the NIST security level 1. To conclude, we implement a configurable butterfly core, which can be used for entity, inverse entity, and pointwise multiplication operations. We also reduce the latency of the Ketchup and sampling units using the highly parallel architecture. Using these results, we can achieve 96% efficiency improvement in terms of the area time product compared to the best previous ASIC implementation of the Kyber. Our implementation in the NIST security level 1 can perform the key generation, encapsulation, and decapsulation of the Kyber in 21, 33, and 50 microseconds, respectively. Although our implementation is constant time, we are going to extend our design by adding some effective side channel countermeasures to protect our design against DPA attacks. Thank you for your attention.